All right, in part one, we talked about space sensible heat ratios and how to determine a proper supply state for your conditioned air. This is part two, system sensible heat ratio and sizing, or how do we achieve proper supply. Last time we looked at our space loads and determined our space sensible heat ratio was 0.7 based on the sensible and latent loads in the space. Now let's take a step back and look at other components that relate to our system design as a whole. One other component is going to be our outside air required. So this is our ventilation air. We're not going to be bringing it directly into the space. This is going to be at the system level. It's going to be brought in at the unit and mixed before the air gets conditioned and goes into the space in this scenario that I am mapping. For the sake of our demonstration, let's say that looking at the people and the area of the space, the ventilation required to this is 100 CFM. This intake is going to happen at the unit. We're going to have a mixed ventilation scenario. Let's look at a couple other airflows in the space. So if you remember from part one, we landed at a supply state of, this is about 57 dry bulb. It doesn't have to be this. This is just where I landed in this example. So before I go further, I'm going to recalculate my primary supply based on this 57 dry bulb entering state. And so if you look at the sensible heat equation here, rearrange to solve for CFM, 72 minus 57 now, that's our delta T, and that's going to yield 425 CFM. So that's 425 CFM being supplied. Just to spice things up, I also am including, say, 75 CFM of required exhaust in the space, which means the return that is left is 350 CFM. So now we have our design airflows. We got 425 primary supply, there's exhaust, which leaves 350 for return, and we also know we have an outdoor air requirement of 100 CFM. Time to look at the system, the configuration of it, and plot those points on the psych chart. Let's plot this one process at a time, looking at both the psych chart and the unit configuration itself. So this kind of package unit, we're going to have the outside air intake right here. We already determined we need 100 CFM of outside air, and let's just say that in the summer, the outside air lands right about here at 100 dry bulb and 80 wet bulb. Next, we have our return air, and we discovered that the return air CFM is 350. The return air, for all practical purposes, ignoring return duct heat gain and whatnot, is going to be equal to our set point. So we're going to map our return air right here. I'll call this set point or return air. Our supply air, we already determined. That was from part one of the series, and after recalculating at 57 dry bulb, the supply air CFM is 425. 100 CFM of outside air intake plus 350 of return yields 450 CFM. We only need 425. So we have a surplus of 25 CFM. The unit is going to relieve that 25 CFM. It's going to reject that 25 CFM from the return air before the return mixes with the outside air. That way we get the full amount of fresh air that is required. So this is how the airflow math maps looking at the units here, and we've already plotted our outside air state, our return air state, and then our supply air state. Based on this design, we have three processes that are taking place. The first process is air mixing. It's happening right here. Your outside air is mixing with the return. That's going to yield a new state. To plot this on the psych chart, super simple. You just draw a line from your return state to your outside air state, and then the mixed air state is going to land somewhere on this line. Now, where it lands on the line depends on the ratio of outside air to return. A pretty simple and intuitive way to do this is you take the total amount of air being mixed, so in this case it's 425, and then you find the return air ratio, 325. This gives you a ratio of about 0.76, about 3/4, and then you can start with outside air and go 3/4 of the way down the line until you get to your mixed air state. So because we have a higher ratio of return air to outside air, the mixed air state right here is going to be closer to our return air than our outside air. I'm just eyeballing it, but you can actually take a ruler, measure this line from return air to outside air, go 3/4 of the way down, and that's where your mixed air state is going to be. Let's just pretend I eyeballed it perfectly, and this is where we're at. So that's our mixed air state. That's state number one that I have plotted right here. The next process is going to be this cooling coil, which is going to yield state number two. We've already figured out where that state is going to be. Again, watch part one if there's any confusion. We have to bring it all the way down to this point right here. So this is going to be state number two after our cooling coil does its thing. And the way cooling coils work is they're going to cool the air. It's going to be a sensible process until you hit saturation. At this point, this is the dew point, moisture, latent load is going to start being extracted from the air, and then your process starts to follow this curve all the way down until you hit the state that you want. So this is what the process actually looks like: sensible, then sensible plus latent. And the load on this cooling coil is going to be the difference between 0.1 and 0.2. To calculate the load on this cooling coil, we can use enthalpy. That's going to give us the total load on this coil, sensible and latent included. First, we need to find the enthalpy for 0.1 and 0.2. So to do that, here on a psych chart, you have your enthalpy lines. You can draw a line that matches the slope of your enthalpy, and then you can take that line, line it up with your state point, and find the enthalpy for state 1. We're going to be doing the same thing for state 2. So let's go ahead and plot those lines. So for this cooling coil, we're looking at a change in enthalpy, delta H, of about 32 down to about 18. The equation to calculate load is Q total is equal to 4.5 CFM delta H. So that's going to be our 4.5. Our CFM going through this coil is 425. And our delta H is going to be this 32 minus 18, 14. This yields 26,775 BTUs. That is the load on your cooling coil to accomplish this process that we've designed, just over 2 tons. Now, the last process before we get our final supply air to the state that we want is this reheat coil. So that's the process line right here. The supply air is going to be our state 3. This reheat coil is going to bring us from state 2, which is saturated and cold, to a more comfortable 57 degree but still dry air state. To find the load on this reheat coil, we're going to do the same thing. First, we're going to plot enthalpy. This is at about 22. We're going to use that same equation, 4.5 CFM delta H. This is going to yield 4.5, 425 times 4, which gives us a 7,650 BTU load on our reheat coil. So now, in part 1, we determined what is a proper state of supply in order to handle our space sensible heat ratio and actually maintain a set point at the humidity that we want. And here we've looked at the process as a whole, the whole system, where you actually have outside air intake required, which is going to mix with your return. We balance the CFMs so that everything here makes sense, and that informs how we do our air mixing. We end up with these different states. State 1 is the mixed air, which happens after outside air and return air mix. We plotted that. Process number 2 is the cooling coil, which yields state 2. And we plotted that on the chart. We found the enthalpies to determine the actual total load on this coil to achieve this design. And then that last process was the reheat, because we wanted this to be dehumidified, dried, and still at a comfortable supply temp. That is the same process where we found the enthalpy for state 3. We take the change in enthalpy between state 2 and state 3 using this equation. We end up with all the psychrometrics we need for this process, and we've got the load on both this cooling coil and then also on this reheat coil. Everything is looking good. Okay, now that we've got our coil loads, those are the big numbers that we need for selecting our equipment. The last piece is, how do we determine the system sensible heat ratio? It's different from the space. Part 1, we started with space SHR. Now, what is the SHR for these coils? And we look at them one coil at a time. For our cooling coil, we can do the same method that we did with space sensible heat ratio, but we'll do it backwards. For my cooling coil SHR, I can draw a line from state 2 to state 1. There's a slope there. You'll notice that slope is different from my space slope because we have a holistic system design. We have this outside air incorporated, this mixing incorporated. Now, I can take this line and I can plot it on this compass going straight through the midpoint to find out what is my SHR. And right here, my cooling SHR is about 0.5. We can do the same thing for our heating process, which is from state 2 to state 3. This one is easy because this line is perfectly horizontal. I don't even need to copy it. If I look at this compass right here, a perfectly horizontal line represents an SHR of 1. That just means it is a 100% sensible process. There's no change in the absolute humidity of the airstream. And with that, you now understand the difference between your space sensible heat ratio and your system sensible heat ratios, how it all ties together, and how to size your equipment. So understanding this is crucial to going beyond just doing rote load calcs and understanding theoretical loads and actually seeing how it affects your system and how your system configuration and design and airflows and psychrometrics affect your coil load, how to do it all properly so you can be confident that, all right, I've got my loads, but now I actually have coil sizing based on the conditions that I want to meet. So I hope this is helpful. If you enjoyed this, or if you think of an engineer who would appreciate this, please forward it along. And if you have any questions, you can always reach out to me, and I'm happy to chat further. Enjoy.